So today we're going to start looking at organic chemistry at AS level, and we're going to be following the AQA modules and course. And to start this first lecture, we're going to have a look at something which has got a slightly odd name, which is nomenclature. And really this is just a fancy name for how we name things, so you could also call it naming. And so this is all about naming organic molecules and organic reactions and how we describe them, so that it's the language really that organic chemists use to describe what's happening in their field. So we're going to start off by looking at the simplest organic molecule. And organic molecules are all around us, and they feature in a huge range of different places, and they pop up all over your life. Sometimes you realize, maybe sometimes you don't, but all sort of synthetic plastic materials, drugs, medicines, fabrics, organic molecules really are everywhere. And so we're going to start with the simplest organic molecule, which is methane. You might have heard of methane. Methane is a slightly smelly gas. It's a greenhouse gas. And methane has got one carbon atom in the middle, so we draw that with a C, which is the elemental symbol for carbon. And then it's surrounded by 4 hydrogen atoms. So I draw these here as H's. And this is the simplest organic molecule. It's the smallest. It owns only one carbon, and there's no what we would call functionality to it, which means that all of these bonds are simply hydrogens. Now you'll notice that carbon has got 4 bonds. So there's, if I switch to a different colour, there's one here, there's one here, there's one here, and there's one here. So there are 4 bonds for carbon. Whereas hydrogen, which is here, each hydrogen only has 1 bond. So hydrogen is 1 bond per atom. 1 bond per hydrogen. Whereas carbon was 4 bonds per carbon. And you'll notice in organic chemistry that this is always the case. Or pretty much always. So carbon nearly always has 4 bonds. We've already covered that. Hydrogen has 1 bond. Oxygen always has 2 bonds, sometimes 3 and sometimes 1, but normally 2 bonds. Nitrogen has 3 bonds normally. And fluorine or chlorine or bromine all have 1 bond. Now of course there are a few exceptions to this, but most of the time, if you're not sure how many bonds to give something, this is a good place to start. So this table is really central to a lot of the work we're going to do around organic chemistry. So if a molecule maybe looks a little bit wrong, just have a quick check and see how many bonds everything has. And normally this will be the case. So the one that's most often not the case is probably oxygen and then nitrogen, which occasionally have slightly different bonding numbers. But in uncharged molecules, that's molecules without a plus or a minus on them, you will normally see these atoms bonded in organic chemistry with these number of bonds. And all of these bonds are covalent bonds. And you should already know what a covalent bond is, so I'm not going to cover that here. So we're looking at methane here, and you can see here that methane has got, as we say, 4 hydrogen atoms surrounding a single carbon atom. And we draw this flat, although it's not really. It's actually a tetrahedron, which is like a triangular based pyramid with the carbon in the middle and the hydrogen on each of the corners. So if I draw it as it would be in real life, you'd have the carbon here, there'll be 1 hydrogen straight up, 1 hydrogen flat over here, and then there'll be 1 hydrogen kind of sticking out of the paper, so we draw this like a triangle to show it coming towards you, and then the final hydrogen will be going away from us, so we draw that with a dashed line like that. So this is the actual shape around the carbon. You don't need to remember this is just to interest you, and in case you're wondering. But this is the shape around the carbon atom, so it's called tetrahedral. And it's called methane, and if I add 1 more carbon atom, so if I now have 2 carbon atoms joined by a covalent bond, and I again surround them with hydrogens, don't worry, if you're getting bored of drawing hydrogens, it's going to stop soon, don't worry. So here we have 2 carbon atoms and we have 6 hydrogen atoms. Each carbon atom has 4 bonds and each hydrogen atom has 1. This molecule is called ethane. And so there we've got one carbon atom is methane. So I'll just call that CH4 for now. Methane. Ethane, which is the one I've just drawn here. So this has 2 carbon atoms, this has 1 carbon atom, 1 carbon, 2 carbon. The next one, if I go to 3 carbon atoms, and I'll just quickly draw it for you, which would be C, 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 and then hydrogens all the way around it. I'll not draw in all the hydrogens, but there are hydrogens on each of these bonds. This would be called propane. And if I keep going, if I go to the 4th one, 4 carbons in a chain, this would be called butane. And if I go again and go to 5 carbons, then it's called pentane. And if I go up one more, I need the next row here, and 6 carbons, this is called hexane. So you might have spotted that for the last two, suddenly it started to look a little bit sensible, because pent is like pentagon, so that's 5, and hex, like hexagon, that means 6. So these prefixes, hex and pent, sort of start to make some sense at this point. But these first 4, meth, eth, prop, but, are perhaps not that obvious. And so you do just have to remember these. There are language origin reasons why these are the case, but I don't want to go into that now. So just remember that meth is 1, eth is 2, prop is 3, and but is 4. And this naming system propagates through all of organic chemistry. So it doesn't matter whether this is propane, like I have up here, or whether I add an oxygen on the end of it and a hydrogen, and this makes it propanol. It's still prop at the beginning because there are 3 carbon atoms. So when we name things in organic chemistry, we typically start with the number of carbon atoms in a single continuous chain, and that's the root of the name. So if I give you another example, if I draw here carbon, 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 and then I add in all my hydrogens around this, which again I'm not going to do, and then I put an oxygen here with a hydrogen next to it. Remember, all of these other ones have got hydrogens on them, etc., but I'm not going to draw them all. So if I've now got my oxygen and my hydrogen on the 2nd carbon, this one is called butan. So there's the but because there are 4 carbons, and then it's butan 2-ol because the ol, the alcohol part, is on the 2nd carbon here. And we'll go into more detail on all of these different compounds and these functional groups is what they're called. This is a functional group at a later stage. But for now, just remember that the number of carbon atoms in the chain goes 1 is methane, then ethane, propane, butane, pentane, hexane. And from then on, if you want to, you can carry on. But for this syllabus, you just need to be able to go up to chains of 6 carbon atoms. One more thing to point out is that if you put them in a ring, so if I have carbon like this in a ring, 6 carbons, this is called cyclo because it's like a cyclical thing. It's a cycle, it's like a wheel, cyclohexane. And I need to draw in all the hydrogens again on here. So each carbon has 2 hydrogens, which I haven't drawn because I'm being lazy. But I'll draw you a couple just to show you. So hydrogen, 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 and now you can see why this gets boring. Hydrogen, 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 hydrogen. I may as well finish now. Hydrogen, hydrogen. Okay, there we go. So this is the fully drawn out cyclohexane. I'm just going to get rid of these hydrogens actually now because they're getting a little bit confusing. So you get the picture, yeah? There's hydrogens all the way around, and this is called cyclohexane. So the same thing would be cyclopentane, cyclobutane. If it's in a ring, then you add a cyclo at the beginning before the prefix, so you get cyclohex, or cycloprop, or cyclopent. And so you need to be able to use these naming conventions, anything up to 6 carbon atoms in either a chain or a ring. So now let's look at the different ways we can display this, and we're going to use, to start off with, we're going to use this molecule I've got in the middle here, which is my butan 2-ol, so this guy. And I'm going to start off by drawing this out fully, so I'm not going to take any shortcuts here at all. This is going to be a little bit boring, and I'm sorry about this. But bear with me, because it gets better, I promise. It gets exciting even. So I'm going to start with my oxygen down here. This has got the hydrogen coming off it. Remember, hydrogen always has 1 bond, oxygen has 2 there, so that looks about right. Then all of these carbons will have 1 hydrogen coming off, have hydrogens coming off them, and each hydrogen has 1 bond. So if I carry these on and finish them off, wow, there we go. So this is called the displayed formula. And that means we show all bonds. So I've not missed out any bond here. I've drawn every single one. I've drawn all the atoms as well. So I could also show all the bonds and atoms. So that's the first way I have of showing you how to draw this butan 2-ol molecule. I'm going to do a different one now, which might look a little bit odd, and then I'll explain what I'm doing. So here's butan 2-ol, drawn a different way. This is still butan 2-ol. It's still this molecule, and it's exactly the same as this molecule. So I've not changed the molecule, I've just changed the way that I've drawn it. And you'll notice here I've got this chain which bends. And every time there's a bend, or every time the chain ends, there's a carbon atom, but we just don't draw it. So if I draw those on top of here now, and I'll use yellow or green, so carbon here, carbon here, carbon here, and carbon here. So we don't draw those, but we know that they're there. Every time the chain turns a corner, or every time the chain ends, there's a carbon atom that we don't draw, so I'll remove them now. Every carbon atom is what we would call saturated, and that means that it's got as many hydrogen atoms as it's allowed to have. So this one here has got 2 hydrogen atoms to make it up to 4 bonds. So you can see I've got 1 bond along here. Let me switch to a different colour. I've got 1 bond along here, I've got 1 bond along here, and then I've got the 2 bonds to the hydrogens. So if I go to this one at the end, this one has 3 hydrogen bonds because it already had 1 bond here. So you always just make it up to 4. And again, these aren't drawn. So I've drawn them here for you. So hydrogen, hydrogen, hydrogen here. This one at the top next to the oxygen, that has a hydrogen. At this end, you get 3 hydrogens. But as we said earlier, not only is it extremely boring to draw lots of hydrogens, but it also makes the molecule really, really messy. And if you start to get a really big molecule, then this can get really confusing. So we don't draw those hydrogens as well. So let's remove all of those and go back to the molecule as we had it originally. So I get rid of all of my hydrogens, all of my red lines. So this is butan 2-ol. So once again, if the main line changes directions, there's a corner, that means there's a carbon. And when the line starts or ends, that means there's a carbon. And then you add hydrogens to all the carbons to make them up to 4 bonds. All of the functional groups have slightly different rules for how you would draw them, but alcohols you just draw like this, OH, and you don't draw the bond between the O and the H. Now I know what you're thinking, hang on a minute, this is a hydrogen, you told me not to draw hydrogens. Yes, I did, and it is a little confusing, so I should apologise for chemists, but basically you only don't draw the hydrogens that are attached to carbons, and this hydrogen is attached to the oxygen. So this one likes to be drawn. Draw me! But we don't draw all the rest of them. Okay, and this is called the skeletal formula. And you can kind of see why, because it looks like a little bit like a skeleton. It's got like just the backbone and nothing else, just the bare bones, the absolute minimum you need to understand what the compound is. So there we've got skeletal formula and we've got the displayed formula, and they're really 2 opposite ends of the spectrum in terms of complexity and simplicity of drawing. The skeletal formula is the one that is used most often in chemistry and organic chemistry. This is really the way that organic chemists communicate with each other. So this is used most commonly. So this is the skeletal formula. Let's put some lines in. This one is the displayed formula. And then we're going to have a look at some other ones as well. So let's have a look now at the structural formula. Structural formula. And this is very similar to the displayed formula, so I'll go through quite quickly. So you'll notice that I'm still here, I'm still drawing out all of the hydrogens. And a couple of different ways of doing this. You might notice there, I've done something differently to the displayed formula. I didn't draw the bond between the oxygen and the hydrogen. So a structural formula is like a halfway house between the two, so you're allowed to sort of abbreviate some things, the oxygen and hydrogen. If you're asked to give a structural formula and you draw all the bonds, you'll not get it wrong, but you can start to abbreviate some things like the OH. And if I make this a little bit more complicated and I turn this end carbon into a carboxylic acid, which we'll get to later, which has this sort of structure, then you might be able to draw this instead at the end of being that. You could just draw that as being COOH. So structural formulas allow you to have certain abbreviations. But a structural formula is very similar to a displayed formula, but just a little bit quicker to draw. But realistically, most of the time, organic chemists will be working with skeletal formulas and won't use structural or displayed formulas unless they're trying to show something really specific. So let's move on to another example then. So we've done displayed formula, skeletal formula, and structural formula. We're going to have a look now at molecular formula and empirical formula. So if we're using butan-2-ol, then the molecular formula of butan-2-ol is you just write down the number of each element, how many atoms there are, and then you put the number down next to it. So this is the molecular formula. So I've got 4 carbon atoms. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Don't forget the one on the oxygen. So we've got H10. And then I've got 1 oxygen, so we don't draw the number, we just put O. So there's like a little imaginary one here that we don't draw. So this is the molecular formula. And then there's one other, which is the empirical formula. And for this, you just simplify the molecular formula to its simplest form as ratios of each of the numbers. So for butan-2-ol, it's actually exactly the same as the molecular formula. But if we just briefly, I'll pick another one as an illustration here. If we went for, and I'll draw it in its skeletal form, if we went for, instead of butan-2-ol, we went for butan-2,3-diol, which has got two alcohol groups on it like this, then the molecular formula of this would be C4H10O2, but the empirical formula would be C2H5O, because you're dividing each of these to make it the smallest number it can be and still be integers. So the smallest one here is the 2 on the oxygen, and 2 divides into all of the others. So you divide all the numbers by 2, divide by 2, and you get this empirical formula. So the empirical formula is the simplest possible, the lowest ratio of all of the atoms in the molecule. So I've just had to switch to, don't get confused, I've just had to switch to a different example here. So this guy is butan-2,3-diol, and we've just used him as an example to show us the molecular formula difference and empirical formula difference, because with butan-2-ol, the molecular formula is the empirical formula because it can't be further simplified. So there we go. So we've got the empirical formula, the molecular formula, the structural formula, the skeletal formula, and the displayed formula. So these are the key formulas that you need to know to use to describe the molecules that you're showing. And there's one other one that we're going to look at now, and for that I'm going to go back up here. And this is called the general formula. So the general formula. And for this we're going to use this set of alkanes. These are called alkanes, these molecules that have got just carbons and hydrogens on them. Alkanes. And we're going to consider the formula for any alkane of any shape length, any chain length. So methane has 1 carbon atom in it, and that has 1 carbon and 4 hydrogens. Let's go here. 1 carbon, 4 hydrogens. Ethane has 2 carbons, and then it has 6 hydrogens. Propane has 3 carbons, and then it has 8 hydrogens. Butane has 4 carbons, and then it has 10 hydrogens, and so on and so forth. So pentane is 12 hydrogens. So you maybe have noticed a pattern here. And the pattern is that the general formula for alkanes is that any alkane, it's always 2n plus 2 hydrogens. So that means that our general formula can be written as CN H, 2N plus 2, which means for every carbon atom, there are 2 hydrogen atoms, and then once you finish the whole molecule, there's 2 more. So if we follow that through here, so for propane, N is 3. Okay, I'll switch colours and show you this. So here we go, propane, N equals 3. So if N equals 3 in my general formula for alkanes, then I've got C3H, and I've got 2N, which is 6, plus 2, which is 8. C3H8. And if you remember for propane, if I drew that out, I would have 3 carbon atoms and 8 hydrogen atoms. So this is the general formula. It describes any one in the series, and these are called homologous series. So alkanes are one form of homologous series. Other homologous series are things like alkenes or alcohols, and in all cases, the chain length is described by the prefixes that we see here: methane, ethane, propane, butane, pentane, hexane. And the general formula describes any one of that homologous series based on how many carbon atoms it has. And then you can draw those molecules using any of these formulas we've gone through at the bottom. Displayed formula, which shows all of the detail, all of the bonds, all of the atoms. Spare nothing, draw everything. That's the displayed formula. The skeletal formula is the nicest one. It's the prettiest one. It's the one that is the easiest to draw and takes the least time, but it contains all of the information that you need. The structural formula allows you to abbreviate some functional groups. The molecular formula just tells you how many of each atom there are in the molecule, and the empirical formula simplifies that down to the lowest number based on ratio of each of the atoms in the molecule. So this is how we go about naming the organic compounds, and this allows you to use them in your chemistry to communicate with other chemists and to write down what you're doing. So this is really important. And in the next lecture, we're going to start to look at reaction mechanisms. So we're going to start to look at how these different molecules react with one another and how that can change them and how you can create new things from the original molecule that you're starting with.